What's up, everyone? Welcome to Equilibrium Part 4. Today we're going to go over Le Chatelier's principle, and I just know for a fact that I'm going to butcher the name the whole time, but I'm going to try to get through it. So Le Chatelier's principle tells us that when a stress is imposed on a system at equilibrium, the system will work to oppose the stress. So if you have reactants and it's in equilibrium with products and you somehow introduce more reactants into the system will work in a way to minimize that stress, and it'll work to balance itself out and go back to equilibrium. And there's basically going to be three different instances where Le Chatelier's principle is going to take effect. So one of them is going to be a change in concentration, the second is going to be a change in pressure, and the third is going to be a change in temperature. And we're going to go through each of these. So let's start with a change in concentration. Pretend you have an equation where A is in equilibrium with B, and A is red, and B is green. And you have at equilibrium, it looks something like this, and somehow you add A. You add these two A molecules to the system, and so what is the system going to do to oppose the stress? Well, since you added A, the system's going to ask, how do I get rid of A? And the way you get rid of A is by consuming it, and when you consume it, you are doing the forward reaction. So what will happen is that the rate of the forward reaction is going to increase. So at the end, you have less A and you have more B. But at the end, you'll notice that the Kc value is going to be the same. So really, Le Chatelier's principle, when it comes to a change in concentration, works by making sure that whenever you add a stress, the system works in a way that the equilibrium constant is maintained at the end. So at the start, you have a Kc value of 4/4, and you end off with a Kc value of 5/5. So the system goes back to equilibrium, goes back to that exact position in equilibrium, even though you added some stress. In other words, a change in concentration is not going to change your equilibrium constant. Let's move on to the second one, which is a change in pressure. Imagine you have a system where A is in equilibrium with B and G. The thing you have to realize here is that the number of particles that are in the system are going to have a massive impact on the pressure of the system. So the more moles you have, the greater your pressure is. If you had a lot more products and reactants, your pressure in the system would be much higher, since the products are more moles than the reactants. So if your system had too much pressure, you'd look to the side of the equation where there is less moles. So let's say in this system, it's too much pressure. We need to decrease the pressure. Would you increase the forward reaction or would you increase the reverse reaction? Well, you would actually increase the reverse reaction because the reverse reaction decreases the number of moles. On the other hand, if you were trying to increase the pressure, you would increase the forward reaction. Now, an important distinction is between phases. So if you had something like A, which is a gas, and it's reacting with D, which is a solid, and it's in equilibrium with B and C, the only things that would matter here are going to be the B, C, and the A. And that's because gases take up a lot more volume than solids. So when looking at the number of moles on each side of the reaction, you should only look at the gaseous molecules. So in this case, if you were trying to decrease the pressure, you would still increase the reverse reaction. And similarly, a change in pressure, like the change in concentration, does not change the equilibrium constant. The system works to revert back to its initial equilibrium condition, and so really a change in pressure is not going to change your equilibrium constant. So in summary, pressure is going to be proportional to the number of moles, and it's going to be inversely proportional to the volume. So let's say you want to increase the pressure. Well, if you wanted to increase the pressure, you could either increase the number of moles or decrease the volume. If you wanted to decrease the pressure, you would decrease the number of moles or increase the volume. Now that volume bit is pretty important. So remember, pressure is inversely proportional to volume. So if you had a system like this where A is in equilibrium with B and G, and at equilibrium it looked like this, but you added some gas to it. In this case, we added argon. Would Le Chatelier's principle work in this scenario? You might be tempted to say yes, because shouldn't increasing the number of gaseous particles increase the pressure? Well, no, and that's because inert gases are not going to affect equilibrium. Argon is an inert gas, meaning it does not react at all with basically any element. And so your system kind of stays the same. Your system is still this. Your system is not affected by the argon, so the pressure in your system is still the same. If you add inert gases into a system, it's not gonna, Le Chatelier's principle is not gonna take effect because again, the inert gases do not affect the system itself. Let's do a bit of practice with this pressure bit. So for which of the following reactions would the yield of products at equilibrium not increase at a higher pressure? So essentially, if we were to increase the pressure, in which of these following reactions would the yield of products not increase? So let's go through each of these. For this one, we have two gaseous particles on the reactant side and two gaseous particles on the product side. So it's kind of an ambiguous case. We can leave that for further analysis once we get through the rest of the answer choices. Let's look at B. So B has two gaseous particles on the reactant side and one gaseous particle on the product side. So if we increase the pressure, well, the system would ask, how do I decrease the pressure? In this case, you could decrease the pressure by having more products. You could increase the forward reaction, and so the yield of your products would actually increase. So B cannot be the right answer. Similarly, in G, you have four gaseous particles on the reactant side and three on the product side. So if you wanted to decrease the pressure, you would have more products. You would increase the forward reaction. So C doesn't make sense. And then D, you have four gaseous, and I think this is a gas too, so five gaseous. And then on the product side, you have two gaseous. Again, you have less gaseous on the product side, so you'd increase the concentration of the products if you wanted lower pressure. So the only thing that we're really left with is our ambiguous case from before, where we have two gaseous on the left-hand side and two gaseous on the right-hand side. And so that would actually be the right answer in this case. So our answer is, in fact, A. Let's move on to the last one, which is going to deal with a change in temperature. So if you have a system where A is in equilibrium with B and you know your change in enthalpy is positive 100 kilojoules per mole, well, you could actually write your equilibrium expression a bit differently. You could write A plus heat is in equilibrium with B. And this is really important because it kind of signifies heat as a reactant. Now, if you ask yourself, if we increase the temperature on the system, what happens? Well, if you were to increase the temperature, well, what you're really doing is you're increasing heat. And remember, once you do something to the system asks, how can I minimize that change? So if you add heat, the system's going to ask, how do I consume heat? Well, in this case, you would consume heat by speeding up the forward reaction. So in this case, if you were to increase the heat, the forward reaction would increase and more products would be produced. On the other hand, if you had A is in equilibrium with B, but in this case, the change in enthalpy was negative 100 kilojoules per mole, well, your equilibrium expression would look something like this, where heat is actually a product. And if we were to increase the temperature of this system, what happens? Well, we need to decrease heat. And the way we do that is by consuming heat, which means we speed up the reverse reaction and increase the number of reactants. So seeing heat as a product or a reactant is really going to help us determine what's going to happen if we were to increase heat or decrease heat. But the difference in change in temperature is that changing temperature is going to change the equilibrium constant. So do be wary of that. Let's do a little practice problem. The following endothermic reaction is at equilibrium in a sealed container. Which of the following changes would result in an increase in the number of moles of PCl5 present at equilibrium? Well, since we're told that it's an endothermic reaction, we can treat heat as a reactant. So we can have PCl3 plus Cl2 and heat as a reactant, and that's all going to be in equilibrium with our product, which is PCl5. And let's go through the two answer choices here, or the two little options here. Which of the following is going to result in an increase in the number of moles of PCl5? So which one of these is going to increase the forward reaction? First of all, increasing the temperature. If we increase the temperature, the system asks, how do we decrease the temperature? How do we get rid of heat? Well, you get rid of heat by increasing the forward reaction. And the forward reaction is going to produce the product. So yeah, increasing the temperature would work to increase the number of moles of PCl5 present at equilibrium. 2, increasing the volume. Increasing the volume in this case would work to decrease the pressure. And if we decrease the pressure, the system asks, how do I increase the pressure? Well, you increase the pressure by having more gaseous molecules. And there are more gaseous molecules on the reactant side than the product side. So what happens is that the reverse reaction speeds up. And the reverse reaction works to increase the number of moles of reactant. and decrease the number of moles of PCl5, so this would have the opposite effect of what we want. So the only answer choice that works here is going to be one only, which is answer choice A, and that is the right answer. Okay, that's all I have. I hope you learned something, and I'll see you later for part 5. Thank you for watching.